Hey everyone, in Chemistry 40S and Chemistry 40SH Planet. It's Dr. Carroll here. We are now looking at the first lecture from Unit 7, Redox and Electrochemistry. What's up, docs? Redox is up. So Unit 7, Lecture 1. Redox is short for reduction and oxidation. What is that all about? Well, part of it is about batteries. Many of our modern devices are powered by batteries, as it says here on page 1 of the booklet. If you don't have the booklet, look on our website and download it. If you still don't know where it is, send me an email or an EDSB message and I'll send it to you. Many of our modern devices are powered by batteries, portable storage devices for electrochemical energy that is produced by product-favored oxidation reduction reactions. So in a battery, we are converting chemical energy into electrical energy. There's a desire to grab electrons at the cathode from the anode in a battery, and if we find some way to push those electrons through a wire, a conductor, we can create a circuit and we can do work. And some of you who are taking physics know all about this. So in batteries, electrons from a product-favored redox reactions are generated and transferred as an electrical current through an external circuit. Oxidation reduction reactions are an important class of reactions. You know that I just had a striped fudge cookie. It was very good. That is combustion. That will give me the energy to get through this lecture today. And if I have a second one, then I'll get through the lecture tomorrow. Redox reactions involve the transfer of electrons from one reactant to another. So just as in our previous chapter, chapter 6, with Brownstein-Lowry acid-base reactions, we looked at transfers of protons. Here we're looking at transfers of electrons. And that's just what it says there. It's a matched set. You can't have oxidation without reduction. There's no I in team. So here's some vocabulary that we're going to use. Electrochemistry is the study of the relationship between electron flow and redox reaction. Reducing agent is an atom, ion, or molecule that causes the reduction of another ion, atom, or molecule. So it acts on something else. An agent acts on something else. If you're using some bleach, it's a cleaning agent. It acts on the surface that you're cleaning. So a reducing agent, it itself, Ra is short for reducing agent, Ra is oxidized. It causes something else to be reduced, something else to gain electrons. Electrons are negative, so when you're gaining electrons, you are being reduced. Oxidizing agent is an ion, atom, or molecule that causes oxidation of another ion, atom, or molecule. It itself, the OA, the oxidizing agent, is reduced. It causes something else to be oxidized, something else to lose electrons. And here we have oxidation is the loss of electrons. Reduction is the gain of electrons. There's a different definition for organic chem about hydrogens and oxygens. You can look that up if you want, but we're going to use this more general definition. Oxidation is the loss of electrons. Reduction is the gain. Okay, oxidation refers to loss. Reduction refers to gain. Each reaction by itself is called a half reaction, simply because we need two half reactions to form a full reaction. So here's our little mnemonic device. It has nothing to do with oil, but people like to use it anyways. Oil rig. So oxidation is loss of electrons, reduction is gain. I've also heard Leo the German and Leo the lion says grr. And then one of my comics strips in my All This Science blogspot.com. You should all look at that every now and then. If Leo the lion says grr, Tony the tiger says, you guessed it, great. And then there's a picture of Tony the tiger in my cartoon. Okay, so we have here that we have oxidation. X goes to X plus an electron. So that is showing that the reactant is oxidized. It loses electrons. It becomes an ion. It's also the reducing agent because it can reduce another reactant by giving the other reactant the electron. Y here gains the electron. You see electron on the reactant side, so Y gains an electron, so it is going to be reduced because it gains an electron. and Y is also an oxidizing agent because it causes X to be oxidized. So if I put them together, I get X plus Y goes to X plus Y minus. So there's my two half reactions. This is called the OHR, or the oxidation half reaction, and this is called my RHR, my reduction half reaction. If I put them together, I get my overall redox reaction. So X is oxidized and Y is reduced. Okay? So let's learn a bit about oxidation numbers, because they help us in less obvious situations to decide what's oxidized and what's reduced. That's important for balancing redox reactions, it's important for titration, it's important for calculating voltages in electrochemical cells. So in considering redox reactions, you must have some sense of the oxidation number. It's called the effective charge, but really it's just a fictitious bookkeeping device that still helps us decide what's oxidized and what's reduced. An increase in oxidation number, sometimes called oxidation state, by the way, means the substance was oxidized, and a decrease means the substance was reduced. The oxidation number suggests the tendency of a compound to be oxidized or reduced. Here's the rules, and they aren't necessarily the same as ionic charges. Okay, so there, we already said that. Here comes the rules. Now I'm never going to ask you to recite all the rules. You're going to apply them. So the first rule is, there's no fight club. No. The first rule is the oxidation number of a monatomic ion, one atom, with a charge, equals the charge on that ion. So sodium plus, the oxidation number is +1. Usually put it as a little circle with a number over it, sometimes in a different color. Sometimes you don't use a circle. F minus is -1. O2 minus is -2. The charge, you put the number, then the sign. The oxidation number, you put the algebraic sign, then the number. Chloride's -1, aluminum's 3+. If I was doing calcium ion, 2 plus, the oxidation number would be +2. If I was doing bromide, the oxidation number would be -1. Okay? And that's a pretty easy rule. Rule number 2, the oxidation number of any isolated neutral element or elemental molecule is 0. So all these ones here are 0. If I had lithium, its oxidation number would be 0. If I had tetraphosphorus, its oxidation number is 0. It's an elemental molecule. Its oxidation number is 0. Rule number 3, in compounds, the oxidation numbers of alkali metals is +1. So in NaCl, the oxidation number of sodium is +1. You might guess, and you'd be right, that the chlorine is going to be -1. That's rule 7, where the sum of the oxidation numbers has to give the overall charge on the whole creature combined. It's neutral all together, so it's going to be 0. K2O, each potassium is +1. You don't put a +2 here, you put a +1. Each is +1 and oxygen is -2. So those are alkali metals. Francium fluoride. I used to know francium fluoride. No. Francium is +1. Fluoride is -1. Okay. Rule number 4. In compounds, the oxidation number of alkaline earth metals, group 2 metals, or 2A, is +2. So radium oxide, radium is +2, oxygen -2. Calcium hydride, calcium is +2. Let me write that again. Calcium hydride. Calcium is +2. Oops. There we go. Each hydrogen is -1. Okay. Rule number 5. In compounds, the oxidation number of oxygen is -2. So for example, in H2O, the hydrogen is +1. Let's write it again. H2O. Hydrogen is +1. Oxygen is -2. There is an exception. Peroxides, where oxygen is -1. We won't come across that very often. So, well, I'll do one here. If I look at H2O2, hydrogen peroxide, hydrogen is +1, oxygen is -1. Rule 6, in compounds, oxidation number of hydrogen is +1, except for, I'm going to put in the word binary here, binary metal hydrates. In that classification of compounds, hydrogen is -1. But in just about all the ones we look at, hydrogen will be +1. So in ammonia, that's not a metal hydride. Hydrogen is going to be +1, each nitrogen -3. Lithium hydride is a binary metal hydride. There's only two kinds of atoms, and one of them is a metal. And see, if hydrogen was +1 here, then we'd have a conflict because we already looked at a higher priority rule which said that the alkali metal is +1. So you can't have both of them +1 because we'll see from rule 7 they have to add together to give you 0 because lithium hydride all over is neutral. So hydrogen is going to be -1 in a binary metal hydride. Rule 7, I've already alluded to it. For a given system, the sum of oxidation numbers of the constituent atoms, all the atoms that make up the system, must equal the net charge on the system. So there's H3PO4, hydrogen is +1 from previous rules, and oxygen is -2. So then the phosphorus has to be +5, because we're going to have 5 and 3 is 8. Each oxygen is -2, so 8 and -8 is 0. You can use a calculator if you want, but I hope you don't really need to. H2SO4, hydrogen is +1, oxygen is -2, there's 4 of them. So sulfur has to be +6, so you have 2 plus 6 is 8, plus -8 gives you 0. NH4 plus, hydrogen is +1, each nitrogen is -3, so they add together to give me +1. And sulfate, SO4 2-, each oxygen is -2, sulfur is +6, 6 plus -8 gives me 2-. Okay. Some other side rules, fluoride in a compound. The fluorine in a compound likes to be -1 most of the time. What other ones are there? Aluminum in a compound likes to be +3. Zinc in a compound likes to be +2. Silver in a compound likes to be +1. Those ones we see a lot in redox, so I'm just telling you in a compound those are what they like to be. And sometimes it's good to separate things out. Like if I have something like ammonium nitrate, NH4NO3, think of it as two groups, of NH4 plus and NO3 minus. So NH4 plus, hydrogen is +1, each nitrogen is -3, so that gives me NH4 plus. And then my oxygen is -2, each hydrogen is +5, so that is -1. So I got a +1 and a -1. So grouping them like that helps us assign oxidation numbers. And you see that you can have, even in a compound, different atoms can have different oxidation numbers if they're ionic compounds, and we're looking at the polyatomic cation and polyatomic anion differently. Now that's getting a little advanced, but that is something that we sometimes get over or see. Okay, here we have an example here. What's the oxidation number for sulfur and sulfur dioxide? So oxygen is -2, and then the sulfur would have to be +4. For sulfate, we just said that oxygen is -2, sulfur is +6. So sulfur is in a higher oxidation state, is how it says in the sulfate anion than in sulfur dioxide. So it's more highly oxidized in the sulfite ion. Remember, something is oxidized, it loses electrons, its oxidation number increases. If something is reduced, it gains electrons, its oxidation number decreases. And redox involves the transfer of electrons from a reducing agent to an oxidizing agent. Okay, so something that's oxidized is something that's reduced. And just to show you, not all reactions are redox. Like acid-base reactions of the Arrhenius kind are not. If I go here, I got hydrogens +1, chlorines then -1, sodium +1, oxygen -2, hydrogen +1, and then on the product side, hydrogen +1, oxygen -2, sodium +1, chlorine -1. If I look for changes in the reactants, hydrogen goes from +1, oh, it's still +1. Sodium goes from +1, still +1. Chlorine goes from -1, still -1. Oxygen -2, still -2. So this reaction here, this double replacement reaction, is not redox. So some reactions are redox, some are not. You can have fractions, by the way, for oxidation numbers. Here's N3O4, just to show you. Oxygen would be -2, and nitrogen would be +8/3, right? It's a fictitious number. It still helps us to decide if it's oxidized or reduced. Fractions are allowed. Okay, practice oxidation numbers. We can do these. I'm going to do them really quick, but you might want to pause this video, try them all yourself, and then we'll go through them. Pause. And we're back. Okay, so we go HCl. So I got +1, -1, HBr, +1, -1, H2SO4, +1, +6, -2, H2SO3, +1, -2. What's this one? It's going to be +4, right? +4. Yeah. Okay, that's good. NH4Cl. So think of that as ammonium chloride. So chloride is -1, hydrogen is +1, nitrogen is -3. So it's like NH4 plus and Cl minus. NH3, we looked at that before. +1 and -3. pH3, +1 for the hydrogen, -3. ClF, okay, that's one we haven't looked at, but fluorine is more electronegative than chlorine, so it's going to be -1, and chlorine will be +1. AgCl, halogens, if they aren't fluorine, and there's nothing else involved, they like to be -1. Sorry, I shouldn't say that. They like to be -1 if they can, and then silver is +1. Silver likes to be +1. Silver nitrate, +1 for the Ag, -2 for the oxygen, +5 for the nitrogen. Ag2SO4, each silver is +1. You don't put +2, you put +1. It's per silver. Oxygen -2, sulfur +6. So that's 6 plus -8. It's -2 plus 2 is 0. Good. C6H12O6. Oh, okay, that's a different one. -2 plus 1. So each carbon is 0, and that's allowed. You can have oxidation numbers of zeros even in compounds, and we do in this case. So 0 plus 12 plus -12 gives me 0. PO43 minus, oxygen is -2, phosphorus is +5. SO42 minus, oxygen is -2, sulfur is +6. H3O plus, that's hydronium. We remember that from the acid-base chapter. Oxygen is -2, each hydrogen is +1. N2O5, oxygen is -2, each nitrogen is +5. N3O5, oxygen is -2. So it's -10. So each nitrogen is 3 1/3, or as a improper fraction, 10/3. NO2 plus, oxygen is -2, nitrogen is +5. NO2 minus, oxygen is -2, nitrogen is +3. PbCl2, okay, chlorine likes to be -1 when it hooks up with a metal, so each lead is +2. Okay. More practice on page 4. You can look through that on your own, okay? We've said this before. And now let's jump to the bottom of page 4. So to decide what is oxidized and what's reduced, here we have magnesium plus chlorine for magnesium chloride. So ionic bond formation, ionic compound formation from the elements or elemental molecules, typically in their standard states. So magnesium, notice so the state actually doesn't change the oxidation number. So magnesium is 0, then it goes to +2, so the oxidation number goes up, therefore it is oxidized. There's no such word as oxidization. It sometimes creeps in, but there really isn't that word, so don't use that word, okay? Reduction goes from 0, or chlorine goes from 0 to -1, so that is reduction. So we say that magnesium is oxidized, chlorine is reduced. Chlorine is the oxidizing agent because it's reduced, and magnesium is the reducing agent. So we have labeled everything possible in that first example. It's an identification example. Well, what's here? Page 5. Oh, this is just 1,000 more examples. You can do that to help you get to sleep one night. Okay, on to page 6. When we write redox reactions, chemists typically write out the electrons explicitly for the half reaction. In writing half reaction redox equations. So here's an oxidation. We see electrons are lost. They're given away. They're liberated. So they're on the product side. Transition metals have varieties of oxidation numbers. Lots of them. Always positive, though, for the metals. Copper goes to copper 2 plus 2 electrons. So that's an oxidation. We balance the charges, right? You have the same number of copper symbols on each side. You got a 2 plus for a charge, so you need 2 negatives. So now it's balanced. Here we have a reduction. We got 2 Ag plus 2 electrons goes to 2 Ag. I could just have Ag plus an electron go to Ag, but I'm multiplying through by the 2 here so that we can combine the 2 reactions together and get rid of the 2 electrons. So we're going to combine an oxidation half reaction and a reduction half reaction together to get my overall reaction. Okay, so copper plus 2 Ag plus goes to copper 2 plus 2 Ag. Ag plus is the oxidizing agent because it causes copper to be oxidized, and copper is the reducing agent because it causes Ag plus to be reduced. Some students, by the way, think that the oxidation number depends on the coefficient. It doesn't. The oxidation number of Ag plus is +1. It's not +2, it's +1. The coefficient does not change the oxidation number. Okay, there's some review statements for you on page 6. And so now we want to talk about balancing oxidation reduction processes, and we're going to balance them in acidic environment and neutral environment. Typically, we won't look at a basic environment. That's got to leave something for next course, right? As a summary, here are the steps to follow to balance a redox reaction in acidic solution. Divide into half reactions. Balance, excuse me, for the elements other than hydrogen and oxygen. And then we're going to balance for oxygen by adding in waters where necessary, and then look at the hydrogens and add in H pluses where necessary because it's an acidic environment. And then we're going to balance the charge by adding electrons. Then we're going to multiply to get we're looking for the least common multiple so that the electrons cancel out, combine, cancel, and check. So let's start with an easy one here. In fact, so easy it's already balanced. Look, I got 1 cadmium, 1 copper, 1 copper. Don't worry about the phases. 2 plus is my net charge on the left, 2 plus is my next charge on the right. So easy peasy, that one I didn't need any 7,000 charges, 7,000 ways to solve that one. So that's good. Second one, okay, zinc, the oxidation number is 0. I got an H plus there, so it's +1. I got a zinc 2 plus, so it's +2. And I got a hydrogen, so it's 0. So zinc goes from 0 to +2. So that's oxidation. H plus goes +1 to 0, so that's reduction. So now we can separate them. So my oxidation half reaction is zinc goes to zinc 2 plus. Give a little bit of room on both sides because you may have to fill some things in. My reduction half reaction, H plus goes to H2. So now let's look at the oxidation half reaction. We got zinc goes to zinc 2 plus, so those symbols are good. I know I'm releasing electrons, so they have to be on the product side. And to balance the charge, I got to put 2 of them. So I'm going to put a little B in front of the OHR, not because it's Niels Bohr or that this is a boring topic, but that this means it's a balanced oxidation half reaction. Okay, so it's a balanced oxidation half reaction. And then I have a reduction half reaction. I got a hydrogen there. I got 2 hydrogens there, so I'm going to put 2 H pluses. So now those are balanced, and I'm going to have to balance for charge, so I'm going to put 2 electrons because the right hand side is, with the reduction half reaction, there is no charge on it, so I have to have no charge on the other. They have to be the same on both sides. So that's now a balanced reduction half reaction. And then I can cancel out the electrons. Got 2 electrons on each side. I don't have to do anything fancy with that, and I end up with zinc plus 2H plus goes to zinc 2 plus H2. Okay, so that is one of the simpler ones. Let's try another one here. So aluminum all by itself, oxidation number is 0. Zinc is +2. Aluminum 3 plus is +3. Zinc is 0. So aluminum goes to aluminum 3 plus. So that's oxidation. The oxidation number goes up. Zinc 2 plus goes to zinc. So that is reduction. So my oxidation half reaction is Al goes to Al3 plus. My reduction half reaction is zinc 2 plus goes to zinc. Oxidation, I'm releasing electrons, how much? 3. So that now becomes the balanced oxidation half reaction. Reduction half reaction, I'm going to add in 2 electrons to balance that. So that's now the brr. Now, I can't just add these two together to get the balanced overall redox reaction because I don't have electrons equalized. I got 3 electrons on the right and 2 on the left. So I have to find a way to get the least common multiple of 3 and 2. Well, that's 6. Okay. I used to call this lowest common denominator, but Mr. Stevenson said, no, don't call it that. You aren't doing any division. Call it least common multiple. And Mr. Stevenson is always right. So that's what we'll do. So what I'm going to do is I'm going to take 2 times the Bohr and 3 times the Brr to get this. So 2 times the Bohr, so I get 2Al goes to 2Al3 plus 6 electrons, and 3 times 2, 6 electrons plus 3 zinc, 2 plus goes to 3 zinc. And I'm going to cross out the electrons, so I'm going to get 2Al plus 3 zinc, 2 plus goes to 2Al, 3 plus 3 zinc. And it's always important to check that this works. So I got 2 aluminum symbols on the left, 2 on the right. That's good. Balancing for mass now. 3 zinc on the left, 3 zinc on the right. So that's good. My net charge on the left is 3 times 2 is 6. And on the right is 2 times 3 is 6. So everything's good. So that is a balanced equation. Okay. Now I have some other ones here. 1, 2, 3, 4. Let's just do the second one. You try 1, 3, and 4. Let's try the second one. Okay. So MnO4 minus. Oxygen is -2. Manganese is +7. Oxygen is -2 in the chlorate anion. Chlorine is +5. And so you start by signing oxidation numbers. Oxygen is -2. Manganese is +4. Oxygen is -2. Chlorine is +7. So that's the oxidation numbers. So manganese goes from +7 to +4. So that's a reduction. Oxygen staying at -2. Chlorine goes from +5 to +7. So that's an oxidation. And everything else will fall into play as we go through. So I usually write the oxidation half reaction on the top, just a personal preference. So the oxidation half reaction, I got ClO3 minus goes to ClO4 minus. I'm going to leave a little bit of room because I'm going to have to put some more stuff in there. And my reduction half reaction is MnO4 minus goes to MnO2, and we need some room to put in some other things. So in the oxidation half reaction, I got 1 chlorine on the left, 1 chlorine on the right. That's good. I got 3 oxygens on the left. Oh, but I got 4 oxygens on the right. Now you don't just put in an O. The method that we use, the most common method nowadays, is this. I put in an H2O on the left. And so that means I got the same number of oxygens on both sides. But now I've introduced hydrogen, but it's an acidic environment, so I put 2 H plus on the right to balance the number of hydrogen symbols on the left. I'm going to have electrons on the right. I got to balance for charge. So my charge on the left is -1. So I have -1 and 2 positives, so that's +1. So I got to put in 2 electrons so that I have the same charge on both sides, -1 on both sides. Some students think that, oh, the charge has to be 0 on both sides. No, it doesn't. It has to be the same on both sides. So -1 on both sides is good. So that is my balanced oxidation half reaction. Then our reduction half reaction, we're going to have Mn and Mn is good. We have 4 oxygens. We just have 2 on the right, so I got to put in 2 H2O. So that now gives us 4 oxygens on both sides, and that's good. Hydrogen, I got 4 hydrogens on the right, so I got to put 4 H plus on the left to balance that out. And then the number of electrons is going to be, well, the red is 0, so I got 4 and 1 negative gives me 3. So I got to put in 3 electrons. Okay, let's separate that out. So now I have to multiply the Bohr by 3 and the Br by 2. So to multiply everything through by the Bohr by 3. So I get 3H2O plus 3ClO3 minus goes to 3ClO4 minus plus 6H plus 6 electrons. And for the RHR, I got to multiply through all that by 2. So I get 6 electrons plus 8H plus 2 MnO4 minus goes to 2 MnO2 plus 4 H2O. So I'm going to add those together. So my 6 electrons gets cancelled. And I'm going to have a net of 1 H2O on the product side. Right? I had 4 on the right, 3 on the left, so my net is 1 on the right. I have 8H plus on the left, 6H plus on the right, so my net is 2H plus on the left. And what else do I have? You want to keep them in order. MnO4 minus 2 MnO4 minus plus 3 ClO3 minus goes to 2 MnO2 plus 3 ClO4 minus plus H2O. Now we hope that this is balanced, and we want to check. So I got 2 manganese, that's good. 3 chlorine, that's good. 2 hydrogen, that's good. 2 times 4, 8, and 9, 17 oxygen. 4 and 12 is 16, 1 is 17 oxygen. So everything looks good, but now we got to look at the charge. 2 positives and 2 negatives, so that's 0. And 3 negatives means minus 3 on the left. That's nothing. 3 times minus 1, minus 3 on the right. So give yourself a smiley face and try it on your own and try those other ones. And that is balancing a redox reaction. Then there's some other ones for you to try. So I'm going to let you try those. Or do you want to try? Should we try one more together? Why not? Let's try this one because there's lots of the room on the bottom of page 8. Okay. The dichromite anion is used a lot in oxidation reduction, and we see it here. So let's look at this one. Number 6 near the bottom of page 8. So chromium, well, let's see. Let's get the one we know first. Minus 2. So each chromium is plus 6. 6 times 2 is 12. Plus minus 14 gives you minus 2. The iron is plus 2. Chromium is plus 3. There's plus 3. Isn't it ironic, as Alanis Morissette would say? Okay. So the chromium goes from plus 6 to plus 3, so that's reduction. The iron goes from plus 2 to plus 3, so that's oxidation. So my oxidation half reaction is Fe2 plus goes to Fe3 plus, and my reduction half reaction is Cr2O7-2 minus goes to Cr3 plus. We call these the skeleton or the bare bones of these equations, and now we dress them up and balance everything and make it all work. So we have the Fe is a 2 plus and Fe3 plus. There's the same number of symbols on both sides, so I just need to put in 1 electron, and now it's balanced. The other side, well, I got 2 chromium on the left, and I got just 1 on the right in terms of symbols, so I got to put a 2, not as a subscript, but as a coefficient. So the chromiums are balanced, so that's good. The oxygen, I got 7 oxygen, so I got to put a 7 H2O on the product side. So that works nice. and that gives me 14 hydrogens, so I got to put a 14 H plus here, and I got to put some electrons here. I got to put 6 of them, right? 6 electrons plus 14 H plus, so that's 8 minus 2 is 6. So I got 6 on the left, and 2 times 3 is 6 on the right. So that's now balanced. And we can't add them together though, because I only have 1 electron on the right hand side in the Bohr, 6 electrons on the left hand side in the Bur. So I got to do 6 times the Bohr. So 6 Fe2 plus goes to 6 Fe3 plus 6 electrons. Now I'm going to add them together, and we're going to get anything else cancel out? No. 14H plus 6 Fe2 plus goes to what does that go to? 6 Fe3 plus 2 Cr3 plus 7 H2O. Try to keep it in the order in which the question was asked, and you put the H pluses on the H2Os wherever they go, but on the extreme ends. So let's see, does this work? 6 irons, 2 chromiums. I seem to be missing a chromium here, aren't I? What is it? Cr2, oh, I forgot to put that in, didn't I? Plus Cr2O7 2 minus. So now the chromiums are good. See, that's why you check, right? Oxygens are good, 7. Hydrogens are good, 14 and 14. Charge is 14. Minus 2 is 12. Plus 12 is 24. 6 plus 18 is 24. So we're good. Okay. The next topic is galvanic cells. We'll save that for lecture 2. So try to balance at least 3 or 4 of those equations listed on pages 7, 8, 6, etc. Become an expert, because as you're balancing, you're also getting good practice on assigning oxidation numbers. Sounds good? Have fun.